Week 2, Lesson 9, Interference Fit Stresses, the Press and Shrink Fits. Make a shaft slightly larger than the hub bore it goes into, and forcing them together squeezes the interface. That squeeze is a contact pressure. It stretches the hub into hoop tension, compresses the shaft, and the friction it creates is what lets the joint carry torque with no key. This lesson builds the contact pressure from the interference and works a steel-on-steel fit end to end. Here's the problem. A solid steel shaft pressed into a steel hub, same material, so one modulus. Interface radius 25 mm, hub outer radius 50, radial interference of 25 microns, which is half the 50 micron mismatch on the diameter. Because the shaft is solid, its inner radius is 0. Find the contact pressure, then the hoop and radial stresses in the hub at the bore. Concept 1. What a press or shrink fit actually is. Make the shaft slightly larger than the bore, then force them together, either pressed cold or slipped on after heating the hub. The radial interference gets shared, the bore pushes out, the shaft pushes in, and the mutual squeeze is a uniform contact pressure over the mating surface. That pressure stretches the hub into hoop tension, compresses the shaft, and its friction is what carries torque. No key needed. Shrink fitting is just last lesson's thermal expansion used as the trick to open the bore. Concept 2. Picture two concentric cylinders sharing the interface radius B. The inner member, the shaft, runs from radius A to B. A is 0 when the shaft is solid. The outer member, the hub, runs from B out to C. At the interface, the contact pressure pushes outward on the hub and inward on the shaft. The hub takes it as a hoop tension, largest right at the bore, while the shaft is squeezed into compression. Keep the order straight. A less than B less than C. Concept 3. The general contact pressure. For any two cylinders, even different materials, the pressure is the interference divided by the interface radius times one elastic term A. A collects both cylinders, for each a geometry ratio in the parentheses, scaled by 1 over its modulus, with the inner bracket carrying minus its Poisson's ratio and the outer bracket plus its Poisson's ratio. A comes straight from compatibility. The interference equals how much the bore grows plus how much the shaft shrinks under that same pressure. Concept 4. The special cases that make this tractable. If the shaft is solid, the inner bracket in A collapses to 1 minus its Poisson's ratio. If both parts share a modulus and Poisson's ratio, the whole thing reduces to a single closed form. And if both hold, same material and a solid shaft, you get the starred workhorse. Pressure equals E times delta over 2bc squared times c squared minus b squared. That's the common exam case and the one we'll solve. Just remember it needs both conditions. Setup. First, name the three radii, inner, interface, and hub outer, and confirm A is less than B is less than C. Second, get the radial interference. It's half the diametral mismatch, so a 0.05 mm interference on the diameter is 25 microns radial. Third, pick the formula, general for two materials, the simplified starred form for same material, and a solid shaft. Fourth, pull the modulus from the material table, keep it in megapascals and the radii in millimeters, and the pressure lands in megapascals. Solve. Part 1. The contact pressure. Same material and a solid shaft, so the starred form applies. Plug in, and it comes out to 75 megapascals at the interface. Keeping the modulus in megapascals and the radii in millimeters lands the pressure in megapascals directly. Solve. Part 2. The hub stresses at the bore. The hub is biaxial there. The tangential hoop stress is the pressure times c squared plus b squared over c squared minus b squared, which works out to 125 megapascals in tension. The radial stress at the surface is simply minus the pressure, 75 megapascals in compression. Notice the hoop tension is larger than the contact pressure itself. It's the governing stress, so you size the hub against the hoop stress, not against P. Traps. 5 ways interference fits bite. 1. Delta is the radial interference, half the diametral mismatch, the single most common error. 2. The simplified pressure formula needs both identical materials and a solid shaft. Miss either and you go back to the general form with A. 3. Keep the radii ordered, A less than B less than C, and don't swap the interface and outer radii. 4. Watch the signs. The hub hoop is tension, the interface radial is -P, compression. 5. The hub is governed by its hoop stress, which is larger than the contact pressure, not by P itself. Quick recall. Radii order A, B, C. Inner, interface, hub. The interference is radial, half the diametral. General pressure is delta over B times A. For a same material solid shaft, it simplifies to the starred form. The hub hoop stress is the pressure times C squared plus B squared over C squared minus B squared in tension. And it governs. The radial stress at the surface is minus the pressure. Our steel fit gave 75 megapascals of contact pressure, 125 of hoop tension, and 75 of radial compression. Next up, Lesson 10, the Week 2 capstone. This lesson turned a deliberate size mismatch into stress. The radial interference sets a contact pressure, which loads the hub in hoop tension and the shaft in compression. Lesson 10 pulls Week 2 together, with exam strategy and a set of worked mechanics of materials problems. How to recognize which formula a question wants, and how to move fast under the clock. Everything's at peprepengine.com. Cheat sheet, worked solution, and a quiz attached here.